All right, let's go. Number 10, rogue planets. Billions of frozen worlds drifting through absolute darkness with no star to warm them. The universe contains a population of objects so numerous, so dark, and so utterly hostile that they represent one of the most genuinely terrifying categories of world ever confirmed to exist. They are called rogue planets, planetary mass objects that were either ejected from their original star systems by gravitational interactions during the chaotic early phases of planetary formation, or that formed directly from the collapse of interstellar gas clouds too small to ignite as stars. They wander through interstellar space completely alone, unbound to any star, heated by nothing, illuminated by nothing, drifting through the galaxy in permanent absolute darkness at temperatures only marginally above absolute zero. Current estimates of the rogue planet population in the Milky Way range from tens of billions to potentially over 1 trillion objects, depending on the mass range included in the count. A 2021 gravitational microlensing survey using the Kepler Space Telescope during its K2 mission identified an excess of short-duration microlensing events consistent with a population of rogue planets approximately Earth mass in size, suggesting they may outnumber stars in the galaxy by a factor of several. The universe contains more free-floating, starless worlds than it contains stars, a fact that reframes the concept of a planet from a warm, sunlit object to something far more common and far more desolate. The surface of a rogue planet is a place of unimaginable, unrelenting hostility. With no stellar energy input, the surface temperature is determined entirely by the residual heat leaking from the planet's interior and by the faint warming of the cosmic microwave background, approximately 2.7 degrees above absolute zero. On an Earth-mass rogue planet billions of years after its ejection, the surface is locked in ice hundreds of kilometers deep, under a sky containing no stars bright enough to cast a shadow, in a darkness so complete that the concept of day and night has no meaning whatsoever. The only conceivable warmth on such a world exists deep beneath the surface, where residual radiogenic heating from the decay of long-lived isotopes in the rocky interior might maintain liquid water in the subsurface ocean beneath the ice, an environment analogous to what scientists believe exists beneath the ice shell of Jupiter's moon Europa, but without even the distant warmth of a star in the sky above. Whether such environments could support life is an open question that redefines what habitability means in a universe where most planets have no sun. Number 9. Stellar remnant pairs. Dead stars locked in orbits so tight they are actively destroying each other. Throughout the Milky Way, in numbers estimated in the hundreds of millions, pairs of dead stars orbit each other in configurations so extreme, so violent, and so mutually destructive that they represent some of the most energetically active environments in the galaxy despite containing no living stars. These are close binary systems composed of two compact stellar remnants, combinations of white dwarfs, neutron stars, and black holes locked in tight orbits whose gravitational wave emission is slowly but inexorably bringing the two objects closer together, tightening their embrace across timescales ranging from millions of years down, in the most extreme cases, to hours. The most immediately terrifying of these systems are the AMCAN Venaticorum stars, ultra-compact binary systems in which two white dwarfs orbit each other at separations smaller than the diameter of some planets, completing full orbits in as little as 5 minutes. At these separations, the gravitational interaction between the two objects is so intense that the less massive white dwarf is being physically stretched and distorted by tidal forces, its outer layers overflowing onto its companion in a continuous stream of stellar material. The system is consuming itself, one white dwarf gradually cannibalizing the other, generating X-ray and ultraviolet radiation as the accreted material impacts the surface of the receiving star at a significant fraction of the speed of light. These systems are also among the most powerful sources of gravitational waves in the galaxy, not the brief cataclysmic burst of gravitational radiation produced by a final merger, but a continuous, sustained gravitational wave signal at frequencies detectable by the planned LISA space-based gravitational wave observatory. Several AM-CVM systems are so nearby and so bright in gravitational waves that they are used as verification sources for LISA, guaranteed detections that will confirm the observatory's functionality within hours of its activation. The universe has populated our galactic neighborhood with pairs of dead stars so close together and so violently interacting that they serve as pre-calibrated gravitational wave beacons, broadcasting the sound of their mutual destruction across thousands of light years. Number 8. Giant molecular clouds. Stellar nurseries the size of millions of solar systems that are also the most violent places stars are born. The romantic image of star formation, a gentle, gradual condensation of gas and dust into a glowing protostar, quietly igniting nuclear fusion in the peaceful dark of interstellar space, is almost entirely wrong. Stars are not born gently. They are born in environments of extraordinary violence, turbulence, and competing destructive forces, inside structures so massive and so energetically active that the process of stellar birth and the process of stellar death operate simultaneously within the same cloud of gas and dust, separated by distances measured in light years, but intimately connected by the flow of matter and energy between them. Giant molecular clouds are the largest discrete structures in the interstellar medium. Cold, dense agglomerations of molecular hydrogen, helium, and trace quantities of heavier molecules, with masses ranging from 10,000 to 10 million times the mass of the Sun, temperatures of just 10 to 30 degrees above absolute zero, and internal turbulent velocities of several kilometers per second driven by the energy input of the stars being born and dying within them. The Orion molecular cloud, the nearest major star-forming region to Earth at approximately 1,350 light-years, contains enough mass to form tens of thousands of stars and is actively doing so across dozens of embedded clusters and associations simultaneously. Inside a giant molecular cloud, the environment is defined by simultaneous creation and destruction on scales that dwarf the entire history of human civilization. Massive stars forming from the densest cores of the cloud immediately begin irradiating and heating the surrounding gas with ultraviolet radiation intense enough to ionize hydrogen atoms across distances of tens of light years, carving enormous cavities in the cloud called H2 regions, whose expanding ionization fronts compress the surrounding molecular gas and trigger new waves of star formation even as they destroy the cloud that enabled the first generation. When those massive stars, burning through their fuel thousands of times faster than our Sun, detonate a supernovae after just a few million years, their shock waves propagate through the remaining cloud at thousands of kilometers per second, simultaneously compressing gas into new star-forming cores and shredding the molecular cloud that surrounds them. A giant molecular cloud is not a nursery in the gentle sense. It is a self-consuming engine of creation and destruction, simultaneously building hundreds of new solar systems and dismantling the environment that made them possible. Number 7. X-ray binaries. Neutron stars and stellar mass black holes actively devouring their companion stars right now in our own galaxy. Within the Milky Way, at this precise moment, several dozen stellar systems are engaged in a process of slow-motion stellar murder. In each of these systems, a compact object, either a neutron star or a stellar mass black hole, is gravitationally stripping material from a normal companion star, pulling rivers of superheated plasma across the void between them and consuming it in a process that generates X-ray radiation bright enough to be detected from thousands of light years away. These are X-ray binaries, and they represent the universe at its most predatory, a dead stellar remnant actively feeding on and destroying a living star that cannot escape the gravitational trap it finds itself in. The mechanics of mass transfer in X-ray binaries are as violent as they are precise. As the companion star evolves and expands, or as the compact object's gravity gradually strips its outer layers, material flows from the companion through the inner Lagrange point,
the precise gravitational balance point between the two stars, and spirals inward toward the compact object in a flattened accretion disk of superheated plasma. The inner edge of this disk, orbiting just outside the event horizon of a black hole or just above the surface of a neutron star, reaches temperatures of tens of millions of degrees, radiating X-rays with a luminosity that can briefly exceed the total optical output of the entire galaxy during outburst episodes. Cygnus X1, the black hole whose mass measurement broke stellar evolution models, covered in a previous video, is one example. But the X-ray binary population includes systems like SS433, in which a neutron star or black hole fires twin jets of plasma at approximately 1/4 of the speed of light in opposite directions, precessing like a cosmic gyroscope and carving helical structures into the surrounding nebula visible across thousands of light years. It includes systems like Circinus X1, a neutron star in an extraordinarily eccentric orbit that experiences violent accretion episodes near closest approach and near silence at maximum separation, cycling between these states every 16.6 days with clockwork precision. Each X-ray binary is a demonstration, conducted in real time in our own galaxy, of what happens when the gravitational field of a collapsed stellar remnant is given direct, continuous access to an ordinary star's outer layers. The answer, consistently and without exception, is destruction.
Number 6. Magnetized filaments at the galactic center. Structures hundreds of light years long with no clear origin or purpose. At the center of the Milky Way, within a few hundred light-years of Sagittarius A*, a population of structures has been visible in radio telescope images for decades that has never been fully explained and that grows more puzzling with each improvement in observational resolution. These are the non-thermal radiofilaments, thin, highly elongated structures stretching up to 150 light-years in length, but only a fraction of a light-year in width, oriented approximately perpendicular to the plane of the galaxy, glowing in radio waves through a process called synchrotron emission, produced by electrons spiraling along intense magnetic field lines at near light speed. The first filaments were discovered in 1984 by radio astronomer Farhad Yousefzadeh using the Very Large Array, initially appearing as isolated curiosities in the complex radio environment of the galactic center. Subsequent surveys with improving sensitivity have revealed a population of hundreds of these filaments distributed across the inner few hundred light-years of the galaxy, organized in some cases into parallel bundles and in other cases appearing as isolated structures with no obvious physical connection to nearby molecular clouds or star-forming regions. What produces the relativistic electrons that power the synchrotron emission in these filaments, and what maintains the extraordinarily strong, highly ordered magnetic fields that confine and direct those electrons along the remarkable length-to-width ratios is genuinely unknown. Proposed sources include pulsar wind nebulae, stellar wind collisions, magnetic reconnection events driven by the differential rotation of the galactic center region, and energy injection from past activity of Sagittarius A* itself. A comprehensive 2022 Meerkat radio survey of the galactic center revealed the full extent of the filament population for the first time, identifying over 1,000 individual structures and establishing that they are distributed in a pattern suggesting they are organized by the large-scale magnetic field region of the galactic center rather than by individual energetic sources. The filaments appear to be a permanent structural feature of the galactic center environment, hundreds of light-year-long magnetic highways conducting relativistic electrons through the heart of our galaxy, for reasons that decades of observation have not yet fully revealed. Number 5. Brown dwarfs. Failed stars too massive to have undergone some nuclear fusion reactions in their early lives, but not massive enough to sustain them, cooling and fading into permanent darkness over billions of years. These objects are called brown dwarfs, and they occupy one of the most genuinely strange niches in the taxonomy of astronomical objects, too massive to be planets in the traditional sense, too dim and too cold to be stars, and too numerous to be ignored in any complete census of the solar neighborhood. Brown dwarfs span a mass range from approximately 13 to 80 times the mass of Jupiter.
Objects above the lower limit fuse deuterium, a heavy isotope of hydrogen, in their cores for a relatively brief period after formation before cooling in darkness over billions of years. The most massive brown dwarfs also fuse lithium for a time, providing astronomers with a diagnostic test for distinguishing brown dwarfs from low-mass stars. But all brown dwarfs share a common fate. Without the sustained proton-proton fusion that powers true stars, they have no long-term energy source and simply radiate their formation heat into space, cooling on timescales of billions of years through spectral types that span from conditions barely cooler than the coolest red dwarf stars to temperatures comparable to a warm oven, and eventually to temperatures undistinguishable from room temperature and below. The coldest known brown dwarfs, classified as Y-type brown dwarfs, have surface temperatures below 300 Kelvin, cooler than the boiling point of water. Their atmospheres contain water clouds and, at the very coldest extremes, potentially ammonia ice clouds. They are large gaseous objects several times the mass of Jupiter, floating freely through interstellar space or orbiting at wide separations from nearby stars, with surfaces cool enough that an unprotected human hand could theoretically survive brief contact with their upper atmosphere. And yet, they are the remnants of objects that once burned nuclear fuel in their cores. The brown dwarf population represents billions of cooling stellar failures scattered throughout the galaxy, each one a reminder that the universe attempted to build a star, fell just short, and left behind a slowly fading ember in the dark.
Number 4. Herbig-Haro objects, jets of superheated plasma fired by newborn stars at thousands of kilometers per second through the interstellar medium. When a star is forming inside a dense molecular cloud core, collapsing from a slowly rotating sphere of gas and dust into a protostar surrounded by a swirling accretion disk, the process of accretion is not gentle and it is not symmetric. Material falling onto the forming star from the surrounding disk generates powerful magnetic fields that interact with the rotation of the protostar to launch narrow, highly collimated jets of plasma outward along the rotation axis of the system, perpendicular to the disk plane, at velocities of hundreds to over 1,000 kilometers per second. These jets, among the most energetic phenomena associated with stellar birth, punch through the surrounding molecular cloud at supersonic speeds, driving powerful bow shocks into the ambient medium where the fast-moving jet material collides with stationary or slowly moving gas. The collision zones glow brilliantly in optical wavelengths as the kinetic energy of the jet is converted to heat and radiation, producing the bright, irregular emission nebulae first cataloged by George Herbig and Guillermo Haro in the 1950s, and now known as Herbig-Haro objects. Individual HH objects can be tens of thousands of astronomical units from their driving sources, representing the point of impact between a jet that has been firing continuously for thousands of years and the interstellar medium it is plowing through. What makes Herbig-Haro objects genuinely alarming in the context of stellar neighborhoods is their scale and their indiscriminate violence. A protostellar jet does not aim itself. It fires outward from the forming star's poles based purely on the geometry of the accretion disk, and whatever happens to lie in its path, other gas clouds, other forming stars, other protoplanetary disks, is simply struck by a beam of superheated plasma traveling at a significant fraction of 1,000,000 kilometers per hour. Several observed HH objects appear to be direct impacts between protostellar jets and nearby protoplanetary disks, the jet irradiating and potentially ablating the disk material of a neighboring forming solar system. In the dense, chaotic environment of a young stellar cluster, the formation of one star can actively damage the protoplanetary disks of its neighbors, potentially disrupting planet formation across a wide region of the birth cluster. Solar systems are not built in isolation. They are built in a crossfire. Number 3. Extreme trans-Neptunian objects. Distant solar system bodies whose orbits suggest something massive is reshaping the outer solar system right now. Beyond Neptune, at distances from the Sun measured in hundreds of astronomical units, a growing population of small, icy bodies has been detected over the past 2 decades, whose orbital properties are profoundly, stubbornly anomalous.
These extreme trans-Neptunian objects, ETNOs, follow orbits so elongated that their closest approaches to the Sun keep them beyond the influence of Neptune. Yet their orbital planes and orientations of their closest approach points are clustered in ways that cannot be explained by the gravitational influence of the known planets alone. The clustering of ETNO orbital parameters was the primary evidence cited in 2016 by Batygin and Brown when they proposed the existence of Planet 9, covered in a previous video. But the ETNO population itself, independent of the Planet 9 hypothesis, contains objects whose individual orbital properties are alarming in their own right. Sedna, discovered in 2003 at a distance of approximately 90 astronomical units with a highly elliptical orbit that carries it out to 940 astronomical units at its farthest, has a closest approach distance of 76 astronomical units, far beyond the gravitational reach of Neptune. No known planet could have placed Sedna in her current orbit. Her trajectory requires either a pass encounter with a passing star, formation in the protoplanetary disk of another solar system before being captured by the Sun, or the gravitational influence of a yet undiscovered massive body in the outer solar system. 2012 VP113, discovered in 2014 with a closest approach of 80 astronomical units and an orbit broadly similar to Sedna's, reinforced the case that Sedna is not an isolated anomaly, but a member of an inner Oort cloud population whose orbital architecture has been shaped by influences that planetary scientists are still debating. Each new ETNO discovery adds a data point to a pattern whose explanation remains genuinely contested. The outer solar system, at distances where our observational coverage is sparse and where objects reflect so little sunlight they are nearly invisible to current survey telescopes, may be harboring gravitational influences that are actively reshaping the trajectories of objects in our own cosmic backyard, in ways we have only begun to detect.
Number 2. Superfluid neutron star interiors. The inside of a dead star is a state of matter that cannot exist in any laboratory on Earth. Neutron stars are the densest objects in the universe that possess a surface, a boundary separating an interior from an exterior, as opposed to the pure space-time singularity of a black hole. At their cores, the density exceeds that of an atomic nucleus by a factor of several, reaching conditions where our current understanding of the strong nuclear force reaches the limits of its predictive power and potentially breaks down entirely. But even the outer layers of a neutron star interior, at densities somewhat below the core, contain states of matter so exotic that they have no analog anywhere in the observable universe outside of neutron stars themselves. In the outer core of a neutron star, at approximately twice the density of an atomic nucleus, theoretical calculations predict that neutrons form Cooper pairs, quantum mechanical pairs of particles that condense into a superfluid state, a phase of matter in which flow occurs without any viscosity or friction whatsoever. This neutron superfluid is threaded by an enormous number of quantized vortex lines, microscopic tubes of rotating superfluid around which the angular momentum of the spinning neutron star is distributed. The interaction between these vortex lines and the solid crust of the neutron star produces a phenomenon called a pulsar glitch, a sudden, discontinuous spin-up of the pulsar's rotation rate as vortex lines unpin from the crust and transfer angular momentum outward in a process that has no analogy in normal matter physics. Pulsar glitches have been observed in dozens of pulsars, most famously the Vela pulsar, and their statistical properties provide the only direct observational window into the superfluid dynamics of neutron star interiors. Analysis of glitch behavior in different pulsars has revealed a diversity of interior structures and superfluid properties that theoretical models are only partially able to reproduce. In the most extreme cases, giant glitches involving spin-up events of extraordinary magnitude, the data suggests that the vortex unpinning events propagate through the neutron star interior faster than simple diffusion models predict, implying coherent, large-scale rearrangements of the superfluid vortex structure across a significant fraction of the star's volume. The interior of a neutron star is conducting quantum mechanical phase transitions on a scale of kilometers, detectable from thousands of light years away through their effect on the precision timing of a rotating radio beacon.
It is the largest quantum object in the observable universe, and it is actively demonstrating physics that no terrestrial experiments will ever be able to reproduce. Number 1. The observable universe boundary. The most terrifying wall in existence is not made of matter, but of time. At a distance of approximately 46 billion light-years in every direction, there is a boundary that defines the limit of everything we can ever observe, ever detect, or ever receive any information from. It is called the cosmological event horizon, and it is the most terrifying structure in the universe, not because of what it's made of, but because of what it means. The boundary exists because the universe is expanding, and because that expansion is accelerating. Light traveling toward us from galaxies beyond a certain distance is being carried away from us by the expansion of space faster than it can travel through space toward us. The light from those regions will never reach us, not because of any obstacle, not because of any barrier made of matter or energy, but because the geometry of an accelerating universe guarantees that the space between us and those regions is growing faster than light can cross it. Everything beyond the cosmological event horizon is permanently, irreversibly, and completely cut off from us. Not hidden, not obscured, but causally disconnected, as thoroughly separated from our universe as if it did not exist. The currently observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is larger than the cosmological event horizon, because the universe was expanding more slowly in the past. But every year, as the accelerating expansion continues, more and more of the currently observable universe crosses the horizon and recedes permanently beyond it. Galaxies that are observable today, whose light is reaching our telescopes at this moment, will, billions of years from now, have their future light forever cut off from us by the horizon. Their images will persist in our sky, frozen and increasingly redshifted, as the last photons from those galaxies crawl toward us across an expanding universe. But no new information will ever arrive from them again. In the very far future, after hundreds of billions of years of accelerating expansion, all galaxies beyond our local group will have crossed the horizon. The sky will contain only the merged remnants of the Milky Way and Andromeda and their satellite galaxies, an island universe surrounded by an emptiness so complete that no observation, no matter how sensitive, will reveal that anything else exists. A civilization arising in that future universe with no knowledge of the cosmological observations made in our era would have no way of knowing that the universe contains hundreds of billions of other galaxies. The evidence would have been erased by the expansion of space itself. The universe is not merely large, it is actively hiding most of itself from any observer within it, and the hiding is permanent. I'll be sharing more similar videos in the future, so subscribe to stay tuned.